And we have Vassili Kitsios next.
Yep, thank you.
Let's see if we can test the screen sharing first.
Let's see if I can master the technology.
So,
do you all see the full screen version?
Yes, and I think we can see the cursor also, the mouse.
Yeah, this thing here?
Yes.
Gotcha. All right, sounds good. Alrighty, thank you.
Vassili will be talking to us about data-driven stochastic subgrid turbulence parameterization of geophysical and engineering turbulence.
Great, thank you. I'd like to thank Dimitri, John, and Joanna for the invitation. I'd also like to acknowledge my co-author, Jürgen Friedrichsen, for introducing me to this problem almost 10 years ago now. It's been a pleasure working with him and my collaborators ever since. And also like to acknowledge the funding support from the CSIRO Decadal Climate Forecasting Project. Okay. So the motivation for this work is to reduce resolution dependence in nonlinear systems, and specifically high Reynolds number geophysical fluid dynamics. So as we all know, it's not possible to resolve all the scales of motion for these types of flows. So the large eddies are resolved on a computational grid, and the unresolved subgrid scale interactions need to be parameterized in some way. So the typical approach is the one comes up with a hypothetical physical hypothesis of how subgrid interactions behave, and then produce a subgrid model from that. The present approach, however, we calculate the subgrid model coefficients from a higher resolution reference direct numerical simulation, from which we can later make physical interpretations if we wish. So our stochastic subgrid modeling approach has been successfully applied to 2-level quasi-geostrophic atmospheres, 2-level Coogee oceans, and also 386-level turbulent channel flows. Now these are all truly multi-cal systems with no scale separation. I'll be focusing mainly on the atmospheric application. We could talk about the other two in question time if you like, but just to cover everything, just stick to the one application. So for this atmospheric flow, we're solving the spectral 2-level quasi-geostrophic potential vorticity equation. For those of you that aren't familiar, the potential vorticity, denoted here as Q for zonal wave number M, total wave number N, and on level J, is given by the surface normal vorticity, plus some layer coupling coefficient multiplied by the difference between the stream function on each level. And we solve this over the full triangular wave number set, denoted here by bold T. And the evolution equation for the reduced potential vorticity is given by the Coriolis force plus a drag force parameterizing unresolved boundary layer processes, a term that nudges toward a target climate depending on the season that we're interested in, nonlinear interactions between the waves, and also nonlinear interactions between the waves and the topography, plus a bare dissipation, which we apply to parameterize the unresolved subgrid scale interactions. And we check that the prescribed D0 is in fact consistent with the eddy dissipations calculated from this reference case. And we'll get to that later. So to kind of orient yourself in the physical interpretation of this configuration, it's a proxy for free shear in the troposphere. So this is a 2 vertical level quasi-geostrophic baroclinic model. For this initial case, there's no topography, but we will add topography in for the case to follow. The dominant stability here are Rossby waves centered at a wave number of 14. The energy containing scales, or the flow specific, season specific scales, if you like, they extend out to about the 20th wave number, past which we have a constant entropy flux inertial range with the kinetic energy decaying with an n to -3 self-similar proportionality. So the question is, how can we produce a reduced resolution version of this such that we reproduce the kinetic energy and other scale-based measures across all of the resolved scales? So at the moment, the DNS is 504 wave numbers in 2 directions, but we're going to try and create a lower resolution version at 63 wave numbers initially, and then some other resolutions too. So the data-driven approach that I'm going to demonstrate first requires us to build a database from which we can learn the relationships. So this is to pictorially illustrate our DNS, or our high resolution reference case. This is a triangular wave number plane, and each of these triangles are to represent the nonlinear interactions, the nonlinear triadic interactions. So this is the triangular wave number plane at T0, and then the DNS solves through T1 all the way through to Tn. So this is a time series of triangular wave number planes. At each instant in time, we take a full copy of the DNS field. We then truncate this initial condition at the lower resolution for which we would like to run a lower resolution model. We retain all of those spectral coefficients, but zero all of the others. And in zeroing all the scales within the subgrid, we are killing off all of these triadic interactions, because at least one of the legs, one of the nodes on the leg is zero. So the triadic interaction is now gone. We take a time step with this as an initial condition, and the associated time derivative is the tendency associated with only the resolved scales and only the triadic interactions for those resolved scales. We then go to the next DNS time step, make a copy of that, truncate in the same manner, set all these scales to zero, use this truncated triangular wave number plane as an initial condition, and evaluate its tendency. And this is repeated so on and so forth. So the truncated DNS is never allowed to go off on its own trajectory. It's only ever run for one time step, always snapping back to the DNS field. So when we subtract the full DNS tendencies from the truncated tendencies, what's left over is the subgrid tendency, or the contribution to the full time derivative associated with all of these subgrid interactions that need to be parameterized in our low resolution model. So in its most primitive form, you could think of subgrid modeling as being the task that relates our subgrid tendency to our result field, or Q within the result wave number set. We can then further decompose this subgrid tendency into all of the various classes. So throughout the talk, wherever you see orange, orange is to indicate subgrid, like a subgrid adjective. So for the Eddy-Eddy interactions, these are the fluctuating components, time fluctuating components of our subgrid tendency, and smaller using this stochastic model. So these are relationships between our subgrid eddies, our small orange eddies, and our resolved eddies. So this is like a pictorial illustration of a boundary layer. That's the wall, and this squiggle here is our mean flow, and these are our eddies. The next three interactions all sum together to give you the time invariant contribution to our subgrid tendency. The eddy mean field component are the interactions between the subgrid eddies and the resolved mean field. And this component is proportional to the resolved mean field itself. We have eddy topographic interactions. These are interactions between our subgrid eddies and our resolved large scale topography. You might notice it's kind of undulating large scale topographic features. And these interactions are parameterized proportional to the topography itself. And finally, our mean field Jacobian, which are the interactions between the subgrid mean field, subgrid topography, you notice this kind of high frequency topography, our resolved mean field, and our resolved topography. Now these proportionalities, these are all taken from statistical dynamical closure theory, specifically the quasi-diagonal direct interaction approximation. So in the full closure theory, each of these interactions are represented by non-Markovian integral terms. However, for the application of our data-driven approach, we're assuming that these operators here are time invariant, which allows us to calculate it from data. And we're also assuming that the variance of f hat is also time invariant. As it turns out, this assumption is not so bad, and we're able to achieve our goal in reproducing the statistics across all scales. So how do we go about calculating these coefficients? First, we'll tackle the Eddy-Eddy term. The key point here is that the subgrid interactions are local in wave number space. And this comes out in the closure theory, not in grid point space. So what I'm saying by that, I can write a model for the subgrid tendency at for a particular wave number pair as a function of only that wave number pair. I can't do that in a grid point space. I can't say that the subgrid tendency at a particular point in space is only dependent on that point in space, because it's dependent on the surrounding points in space as well. So for this particular atmospheric application, I'm defining bold Q as being a 2-element column vector, where this is Q for the wave number pair Mn at level 1 and Q at level 2. We're also decomposing this into its mean and its fluctuating component, denoted by the hat here. So we have a unique subgrid model, if you like, for every wave number pair. For the deterministic model, this is a simplified version of the stochastic model here, but we'll just explain the way the deterministic model works first because it's a bit simpler. Our fluctuating component of the subgrid tendency is given, which is a 2-element column vector, is given by this 2x2 matrix, our D net matrix, multiplied by another 2-element column vector, which is the instantaneous fluctuating component of the result field. And just to note that all of these dissipations can be rescaled into eddy viscosities just by scaling it by the Laplacian operator, essentially. So given this functional form, and we know all of the fluctuating components of the subgrid tendencies because of the way that we generated our database by truncating the triangular wave number plane, and we know all of the resolved fields, we just post-multiply this expression by the complex conjugate of our fluctuating component of the resolved field, and then time average across all of the individual instances. We can do that because we're assuming that D net is time invariant. If we then post-multiply this line by the inverse of this covariance matrix, again, this is a 2x2 matrix, it's another 2x2 matrix, we get D net, which is a 2x2 matrix. But again, we have one of these for every wave number pair. The stochastic model, again, this is the way in which we calculate the coefficients is somewhat more involved, but the general point is there are no arbitrary parameters in any of this. All of the model, all of the dissipation coefficients and all of the variances of the stochastic forcing are all determined from the data itself. There is also an equivalence between the deterministic and the stochastic model. The net dissipation is by definition equal to the drain dissipation, which is more dissipative than the net, plus the backscatter dissipation, which is in general negative. Okay, so to give you a feeling for what these coefficients look like, we initially started off with an atmospheric DNS with 504 wave numbers in the zonal and total directions, and we're truncating that back for the moment to a model with 63 wave numbers. So these are the truncated triangular wave number planes. These are the net eddy viscosities, the drain eddy viscosities, and the backscatter eddy viscosities. What you're seeing here is the upper diagonal term, so that's this term here in the eddy viscosity matrix. You notice for all of them, they're very strong functions of n. They're cusp-like. They increase steeply as you go up in the n wave number, but weakly dependent on m. So we can compress that data by averaging in the m direction, isotropizing, if you like. So you'll see that there's negligible eddy viscosity for all of these large scales, and then as we're approaching the truncation waves number of 63, the eddy viscosity increases sharply. Now the extent of these non-negligible eddy viscosities, if you like, is set by the extent of the energy containing range, or the non-self-similar waves. This is because these energy containing scales set how far the legs of the triadic interactions can span. So if I'm sitting at wave number 64, significant interactions of wave number 64 can only really penetrate out to 44 because the energy containing scales are setting the extent of that leg. So we can repeat this process. So that was the profile we saw before by truncating at wave number 63. We're going to truncate at wave number 126 and 252. And this is the bare dissipation that we applied in the original DNS. And you can see, as you would expect, as you're going up in truncation wave number or up in resolution, the amount of eddy viscosity you need is decreasing because you're now trying to represent less triadic interactions. You might also notice that the range of non-zero eddy viscosities is somewhat independent of the resolution that you're running at. So we can non-dimensionalize each of these profiles by dividing by the maximum value of each profile and also its truncation wave number. And that gives us these profiles over here. So that's going from lowest resolution at 63 all the way through to the highest resolution. Yeah, oh, sorry. And in this non-dimensionalized space, you can see that these curves are actually getting steeper and steeper. That's because we've essentially got the same range, but we're dividing by a larger number, a larger TR. The reason that's important is because we can characterize these curves using a power law expression, where this is the maximum value, and this is the steepness of those non-dimensionalized profiles. And then we can see how the maximum value and the steepnesses changes with resolution. So for the maximum value, as we noticed previously, as you're going up in resolution, the maximum values of these eddy viscosities are decreasing. So each of these sets of points are atmospheric simulations truncated to various resolutions. And you might notice the filled points, they're the lower level, and the hollow points, they're the upper level. And when you scale these eddy viscosities or non-dimensionalize them by the entropy flux within the inertial range, then the levels collapse. The diamond points are actually from a completely different atmosphere with a completely different spectra. And when non-dimensionalized appropriately, the maximum value of these eddy viscosities collapses. So this is quite a beautiful result, I think. And these squares here, these are representative of the DNS that was applied, the subgrid bare dissipation that was applied in our DNS. So it's been applied self-consistently with the eddy viscosities that have been determined from it. And again, as we would have expected from the previous diagram, the steepness of these spectral coefficients are also increasing as we're going out in resolution. So the power of this result is now that we've gone and done all the hard work and run high resolution versions of the atmospheric DNS and truncated various different levels, if we want to run a lower resolution version at say 90 wave numbers, we don't need to run the truncated DNS again. We can just read the scaling law expression off the graph. It tells us what our magnitude of eddy viscosity needs to be, and also what the spectral steepness of the dissipation needs to be. And we also have scaling laws for the stochastic terms. So that's all well and good. We've calculated the coefficients. We've observed that within the inertial range in which the kinetic energy spectrum is self-similar, the eddy viscosities are also self-similar. But how well do these eddy viscosity coefficients work in the dynamical model? So here, this is what we've tested. The dashed lines here represent the high resolution version, and the solid lines are the lower resolution LES using our subgrid model. These are simply offset for clarity, but the top one is the true level of the kinetic energy. So here we're using no subgrid model, just as a demonstration of how bad things get when you simply truncate and do nothing in particular. But if you're using either the deterministic or the stochastic form, the full anisotropic coefficients, using the diagonal and off diagonal terms, you get near perfect results. But also when you're using the isotropic scaling laws, so here the scaling laws are only defined for the diagonal terms because when you're truncating past the Rossby radius of deformation, the off diagonal terms are negligible. So in this gross simplification of the eddy viscosities, we can also reproduce the DNS across multiple resolutions. So that was the first part of the talk. The second part is how do we now do the tougher problem when we have topography and also when we're truncating at even lower resolutions in which all of the classes of subgrid interactions are important. The eddy mean field, the eddy topographic, the mean field Jacobian. So what changes? So what we're going to do now, we're going to use the same atmospheric model, but we're also going to apply it to 2 different seasons. The previous set of experiments was applied to an eternal January, if you like. Here we're applying it to a January and also a July basic state. And this is the realistic topography that we're going to be using. Again, the Eddy-Eddy terms are calculated in the same fashion. This is how we calculate the DNet term. And again, the stochastic model, a little bit more involved. We can talk about that later if you like. When we're truncating at a wave number of 31, so this is still within a regime in which baroclinic instability is explicitly resolved. If you recall, the Rossby radius was centered about a wave number of 14. So here, these coefficients are qualitatively similar to what we saw in the previous study. And these are isotropized versions. So the off-diagonal terms, the red and the green, lower in magnitude comparison to the diagonal terms, the black and the blue. The solid lines are for the January basic state and the dashed lines are for the July basic state. So even though the January and July basic states are very different, the subgrid model linking the fluctuating subgrid tendency to the fluctuating field are very similar. And in that way, that coupled with a scaling law behavior that we saw previously, I think accentuates the generality of this result. But when we're doing the tougher problem, as I mentioned before, and truncating even lower resolution at 15 wave numbers, where baroclinic instability is not completely resolved, The dissipation is strongly anisotropic. So what I mean by that, it's a strong function of both N and M. And we also have negative values for dissipation for much of the wave number plane. So negative dissipation means that we need to inject energy into the system. The fact that we're not resolving the dominant instability explicitly in the model means that our subgrid model not only has to dissipate kinetic energy where necessary, it also needs to inject energy back into the larger scales. Because had those subgrid interactions been there, they would have been sending energy to those scales. Okay, so the terms that we haven't seen from the previous study are those that represent the mean subgrid tendency. So our mean subgrid tendency, if you recall, is given by the mean field Jacobian plus the Eddy mean field force plus the Eddy topographic force. And the mean field Jacobian, we can actually evaluate that explicitly by using the truncated mean field as an initial condition, essentially. Once we know what the mean field Jacobian is, we can then calculate the Eddy mean field operator, our D bar here, through a linear regression of QTS minus J minus Q bar. And we've done this over 500 different windowed climate states. And as it turns out, the Eddy mean field term, this D bar times Q bar, has these blocking type structures in the Northern Hemisphere. So it's quite interesting, I think. But for me, I think the most interesting result here is the Eddy topographic force. So once we know the mean field Jacobian, we know the Eddy mean field force, we know the total mean subgrid tendency, we get the Eddy topographic term from the residual. It's just the bit that's left over. So we haven't used the topography to calculate this term at all. It's just, that's the symbolic representation of it. So after all these subtractions and linear regressions, the remainder has an imprint of the topography, which I think is really quite, I really love this result. You can see structures over South America, over the Rockies, over the Himalayas. So what this term is representing, the fact that you're not resolving the small scale topography and the small scale eddies, saying that the interactions between small scale topography and large scale eddies and the interactions between small scale eddies and large topography would ordinarily have been modified your flow field, your time derivative in this way. So it's saying that every instant in time, you need to add this map to your resolved time derivative to ensure that you've captured the interactions between the topography and the eddies. Okay, and then as a test to see if all of these ingredients, when put together, reproduces the high resolution model, for the truncation made at 31 wave numbers, the full anisotropic stochastic, anisotropic deterministic, isotropic stochastic, and isotropic deterministic formulations all reproduce the kinetic energy of the resolved scales. That's so the LES again, this solid black line, the DNS is the dashed line. However, when we're truncating at an even lower resolution within the energy containing scales at a wave number of 15, only the anisotropic variance can reproduce the kinetic energy spectrum to a reasonable extent. The isotropic variance, in which we're averaging the eddy viscosities, it's just too gross a simplification. Okay, so now we can also see what components of this subgrid model are giving us, are contributing to the improvement in the truncated model. So again, the dashed line, that's our DNS case. The solid line here is no subgrid model at all. Again, getting, as you'd expect, crazy results. Energy's increasing at the smaller scales because most of this would have been dissipated, and we're getting a reduction in energy at the larger scales. It's a classic tail wagging the dog effect. When we're adding only the Eddy-Eddy interactions, then we're getting most of the way there. When we're adding in additionally the Eddy mean field force, the Eddy topographic force, and now the mean field Jacobian, we're getting the best results. So the Eddy-Eddy term is the dominant term, if you like, but for best results, you need to include all the interactions. So this is on the basis of the kinetic energy spectra, but also on the basis of the zonal component of the zonal velocity. So this is the east-west winds averaged over all lines of longitude. This is latitude here. The solid line is the DNS. this dashed line is no subgrid model, Eddy-Eddy, and then the circles are everything together. And then finally, looking at the non-zonal stream function, so the time average non-zonal stream function. Again, this is no subgrid model. It's got a correlation with the DNS of 0.5. It's not great. But as you go and add in all the additional components, so the Eddy-Eddy term, eddy mean field, plus topographic, plus mean field Jacobian, we get to a point now where we've got a correlation of 0.962 with the DNS. This is the DNS field over here. Okay, so in terms of concluding remarks, I've presented a general stochastic subgrid modeling approach that represents all of the classes of subgrid interactions. So interactions between subgrid eddies and resolved eddies, interactions between subgrid eddies and resolved topography, interactions between subgrid eddies and resolved mean field, and the mean field Jacobian, which is the interactions between the resolved and subgrid mean field and topography. Note there are no arbitrary parameters in this approach. It's all the data-driven approach calculated from higher resolution reference database. The subgrid coefficients that we've calculated from the reference database have produced lower resolution simulations that have reproduced the statistics across the resolved scales. I've demonstrated today for two-level quasi-geostrophic atmosphere, but we've also done so for quasi-geostrophic two-level oceans. Got some additional slides if you're interested in that. And also 386 level turbulent Navier-Stokes flow, or turbulent channel flow. For the atmospheric flow with topography, the Eddy-Eddy term was dominant, but all interactions are required for best agreement with the DNS. And also for the Eddy-Eddy terms, we've demonstrated universal scaling laws that collapse atmospheric flows across levels and also oceanic flows across levels. And when non-dimensionalized appropriately, the eddy viscosities for the atmosphere and ocean also agree. I might just leave the publications up for those of you that might be interested. Yeah, that's it. Thank you.
Thank you very much, Vassili. Are there any questions for our speaker? I had a question. So you make use of the fact that of the locality of the various interactions in the Fourier domain.
Yep.
Does that mean that sort of then you have to use like a spectral code for your model when you're running things, because otherwise it would introduce sort of large scale communications.
That's right. So in the turbulent channel flow case, I guess the moral of the story is, where possible, exploit any scale decompositions that you can use. So in this atmospheric example that I presented today, it was a spectral code. It was scale decomposed in the meridional and the zonal directions. So for every wave number pair, we had a 2x2 matrix because we had two vertical levels. In the 386 level turbulent channel flow, that was periodic in the streamwise and spanwise directions and used Chebyshev polynomials in the vertical. And so you don't necessarily need to use Fourier. So Chebyshev polynomial is also a scale-based decomposition. So in that application, for every scale triplet, we had a 3x3 matrix where the three elements were the U, V, and W velocity components. So we had a matrix that explicitly represented the subgrid interactions between velocity components for every scale triplet. So if you're in a case where you don't have a scale, it's not decomposable by scale anywhere, then the theory suggests your state vector needs to be all points in space multiplied by all state variables. So it's not tractable. So this approach is, it relies on you having a scale-based decomposition.
To use, let's say, a finite difference code for whatever reason, or some code that is not operating in spectral space, that does basically your conclusion is that I shouldn't be using that type of code. I should be doing things in Fourier space.
Well, there's nothing stopping you from even if your code is finite difference, there's nothing stopping you from doing the Fourier decomposition on the fields after the fact. But using a Fourier code initially would make your life easier. But if the flow configuration is periodic in one direction, you can post-process your data to get your Fourier coefficients.
Okay, thanks.
So I might just add one more point about applying this in physical space. All of those time invariant terms can be applied in physical space. As I showed you those maps. So they don't need to live in scale space. And also those scaling laws, a K of 2 represents a Laplacian operator. And a K of 4, a row of 4 represents a biharmonic operator. So if your code itself is not spectral, but you have access to applying these operators in physical space, then you can apply these scaling laws in physical space. Is that clear?
Yes, thank you very much. So there is a question on the chat from Judith Berner.
Oh, yep.
I'm just going to read it for the.
Sure. Hi, Judith. How's it going?
Just thanking you for the very nice talk. I'm assuming she doesn't have sound, or so I'm just going to.
Oh, yeah, I can ask you in person.
Yeah.
Go for it.
Thanks so much. It was a great talk. And each time I listen to you, I learn something new. My question is, the first portion of your talk, when you looked at this atmospheric model, you're really replacing sort of eddy-eddy interactions, so sort of turbulence with a parameterization, or you estimate that with this really clever way of truncating it while you run the model. I was wondering, could you comment on if you have a more complex model with physics parameterizations as we use it? So if you parameterize convection or planetary boundary layer, do you think your approach would be similarly insightful in terms of learning about sort of these? I mean, there is no longer meaning to triads in that context, right? At least not the turbulence approach. Obviously, they're still interacting wave numbers. I was wondering if you could comment a little on this, or to just sort of rephrase the complete question is, can you go to higher orders of models than you have used? Or why haven't you done that?
Sure, yeah, no, so you definitely can. So yeah, I've demonstrated a QG model today. But the turbulent channel flow, that was a full Navier-Stokes code. And we've also applied it to a primitive equation model. I didn't mention that study today at all. So with much longer state vector, more vertical levels. So it's most definitely doable. There's nothing in the mathematics to say you can't do it. The larger the state vector becomes, the more difficult the sampling problem is. So now you've got more off-diagonal elements that you need to sample properly. So there's nothing prohibiting it working in a convection type application. I guess you just need to intelligently define the variables that are in your state vector. And if you have scale-based, if you can decompose in scale, in say the zonal and meridional directions, then your state vector would be number of vertical levels multiplied by the number of states you have. And then your correlations would tell you, if you have no correlations between certain variables and certain levels, then it's saying that the subgrid interactions don't care about those relationships. So even if I'm working with coupled GCMs now, so I'm kind of doing less work in this space. So I'm fully aware of how messy these things are. But I think even as a diagnostic tool, it would allow you to maybe direct where you might put further development into your subgrid model. You know, if these correlations are telling you, ignore the relationship between moisture on the 10th level and velocity on levels 14 and above. Is that address your question?
Thanks so much. Yes.
Great, thank you.
Can I ask something, like this is more or less along the line of this discussion?
Sure, go for it.
So I really like that picture when you have that, you know, like the flat of the damping coefficient, like when you do the fit, you know, you do the statistical fit.
Which one?
This one, right? That one.
This one here.
Yeah.
Yeah, the self-similar behavior. Yeah.
Yes. So basically, if I understand you correctly, is that you basically try to find this feature that has a functional relationship. In this particular case, is this new coordinate or this isotropic net eddy viscosity as a function of your resolutions, right?
That's right.
And then,
so a priori, we didn't know that this relationship would exist.
Yes, you didn't know this. So basically, in principle, when these things doesn't work, meaning there's possibly it doesn't work, meaning like you really messed up getting a very bad variable, then you'll have something like double like that, right? Then it doesn't work, right? Because it's bimodal, for instance, right? But so long as they have a functional relationship, or they kind of fit to be like a function, then it's, in principle, it should work, right? Is that correct? You sort of like have a big picture like that?
Yeah, I think each of these individual dots represents, just to rephrase for all the other people that maybe didn't get it, each of these dots is an individual experiment.
Yes.
So all of those triangles, each dot represents TR at a different place. I might just go back to that slide.
Right.
So what I'm doing here, I'm sliding this TR up and down to get different resolved wave number planes. So I'm going to get different eddy viscosities every time I do that process. And that requires me to running the DNS over and over and over again. So this is a really laborious task.
Right.
And you get 2 dots on this graph every time you do that. Right? So if you're in, for this first case, if you're in the initial range, kinetic energy is self-similar, we thought it might be the case. We're really happy when we found the eddy viscosities are also self-similar within this inertial range. So now, if
he's probably somehow disconnected.
Lost.
Yeah.
That's fortunate. Oh, there, I think he's joining. He's trying to join.
sorry, can you hear me now?
Yes.
Yes.
Yeah, I'm not sure. I was waving my hand around and like hit leave meeting accidentally. But where are we? Back here. Sorry about that. Can you see my screen again?
No.
Which martial art is that?
Screen?
I think.
Let me turn off all. Maybe we should turn off the video so that to help him.
No, maybe what we should do, because I think we are going a bit. Oh, we could do that.
Yeah, we could turn off the video to help him, and maybe a little bit.
I was going to suggest to basically, say, conclude the session, and and then
we could do that.
Say whoever wants to chat more, because I guess it's getting late in some time zones.
Yep. Sorry, not sure what happened.
Oh. Hello.
Yep, I can hear you. Can you hear me?
Yes.
Yeah, I'm not sure what happened.
Maybe. I was saying that maybe we will wrap up the session now, and we'll stay on Zoom to finish the discussion.
Sure.
So
Sounds good.
yeah, once again, I'd like to thank all the participants, the audience, and the organizers, of course, of the conference for this very interesting day, which I certainly very much enjoyed. And yeah, thanks again, everyone. Just clapping, and hope to see you soon in person as well. So I'll oh, good.